Attention all units. This is your tower director speaking. Welcome to the simulation. If you're tuning into this explainer, you are officially stepping into the control tower for the Cambridge Mathematics 9709 AS and A-level exams. And let me tell you, it is high pressure up here. We are acting as the elite air traffic control for your exam session. And right now, my radar grid is lighting up with incoming heavy aircraft. What are these heavy aircraft? They are the massive, high-tariff differentiation questions. I'm talking about the differentiation of e to the power of x, the natural log of x, and our trigonometric heavyweights, sine, cosine, and tangent. Now, mastering these specific functions isn't just some optional side quest. It is absolutely unequivocally essential for your survival in the exam room. Why? Because this specific topic is a scheduled flight in literally every single examination series. You cannot hide from it, it will not get canceled, and it is coming straight for your runway. But do not panic. Today, as your stress management specialist and tower director, I am going to teach you exactly how to manage this extreme time pressure, prioritize those high-yield marks, and guide these complex problems down for a safe, perfect touchdown.
Our mission objective today goes way beyond just reciting the mathematical rules you've already crammed into your head. You know the basics, I know you do. We are treating this explainer as highly classified insider intelligence. As our lead subject specialist, basically the chief inspector of aviation in this scenario, always emphasizes, we are going to show you exactly what the examiners are looking for on their radar screens. We're taking your mindset from simply doing a bunch of math equations to strategically executing an exam operation. Think of it like this. You aren't just solving a derivative anymore, you are proving to the examining board that your structural safety regulations are up to code, that your logical approach is flawless, and that you deserve every single one of those high-yield marks.
Okay, let's run through our flight plan quickly. We're hitting 1. The differentiation challenge. 2. Core theoretical principles. 3. The procedural framework. 4. Critical analysis skills. And 5. Top examiner warnings.
Section 1. The differentiation challenge. Moving way beyond the basics.
So let's look at the radar grid. When students transition from basic polynomial differentiation to these complex transcendental and trigonometric functions, a massive, system-wide struggle emerges. Why do candidates find applying these concepts to unfamiliar contexts so incredibly difficult? To understand this, I want to introduce you to two operators currently working in our control tower right now. On my left, we have router Alex. Now, Alex knows every formula in the book. But the second a multi-step natural log question pops up, Alex gets totally bogged down in minor, irrelevant algebraic details. He puts the whole problem into an infinite holding pattern, burning precious exam time, and completely misses the bigger picture. On my right, we've got router Sam. Sam has the opposite problem. Sam sees a tangent function and just violently clears it for landing, slapping down secant squared x way too fast without verifying any structural safety regulations, completely ignoring the product rule or chain rule context it's wrapped in. Crash and burn. Cambridge isn't just testing if you know the derivative of sine x in a vacuum. The syllabus explicitly demands that you exhibit a connected conceptual understanding. They are actively testing whether you can take those rules and apply them to completely novel, unfamiliar airspace. It is never about rote memorization. It's about dynamic, real-time application under extreme pressure.
Section 2. Core theoretical principles. Building that rock-solid foundation.
To successfully route these heavy questions without turning into router Alex or router Sam, you need a foundation built entirely on the method mark strategy. In our control tower, method marks are your flight data recorder. The Cambridge exams are specifically engineered to reward the journey, your analytical process, just as much as the final destination. If you only focus on grinding out that final, simplified answer for a massive trigonometric equation, you are leaving an unbelievable amount of points on the table. Examiners want to see your evidence-based reasoning laid out step by step on the page. They are tracking your trajectory. If you make a tiny, insignificant arithmetic error at the very last second of your calculation, but your methodological approach, your glide slope was flawless, you are still going to secure the vast majority of the marks. This is where I need you to implement the fuel-to-mark budget formula. Every mark on that paper represents a specific amount of your time fuel. If a question is worth 3 method marks, you allocate the proportional time to show those 3 distinct steps. You don't burn 10 minutes of fuel on a 3-mark question, and you definitely don't try to solve a 6-mark question in one single fuel-starved line of working. Show the process.
Let's look at the approach layout based on explicit assessment objectives. Examiners are tracking 3 very distinct cognitive domains on their screens. First up is knowledge and understanding. This is your basic foundational check, knowing that the derivative of e to the x remains e to the x, or that differentiating the natural log of x gives you 1 over x. Second is application. This is where router Sam usually messes up. Application means taking those fundamental rules and using them in totally unfamiliar blended contexts, like applying the quotient rule to a fraction that has e to the x in the numerator and cosine x in the denominator. Finally, we have analysis. This is systematic processing and evidence-based reasoning. This is where Router Alex gets stuck overthinking. When you sit down in that exam hall, the paper is actively, deliberately structured to test you across all three of these levels simultaneously. You have to demonstrate you have the knowledge, you can apply it safely to a new scenario, and you can logically analyze the result without losing your cool.
Section 3. The procedural framework. Your blueprint for an absolute zero-fail success rate.
Tower transmission check? Listen up, all units. Before we clear this next response for touchdown, I need to make sure your transponder is fully updated. Hit pause on your mental radar for just 1 second, subscribe to Ace the Exams at the handle at Ace the Exams right now, and turn on all your notifications so you never miss an emergency broadcast. Okay, transponder's verified. Let's resume the simulation. Understanding the theory is fantastic, but when you're under severe time pressure and the clock is ticking down, you need a procedural framework, a blueprint that you can execute automatically. Let's map out this standardized chronological sequence. Step 1. Identify the key elements. What functions are we actually dealing with? Step 2. Apply the relevant principles. Are we using the chain rule, product rule? Step 3. Execute your analysis with abundantly clear working out. Step 4. Verify your results. Does the derivative logically align with the original function's behavior? And Step 5. Present it in the appropriate format. Now imagine you're halfway through Step 3, executing your analysis, and suddenly you hit an unexpected structural block mid-paragraph. You forget where you are. This is when Router Alex completely panics. When this happens, you rely on the sequence. You fall back on your training. Identify, apply, execute, verify, present. Make this sequence pure muscle memory so that even when the exam adrenaline spikes, your hands know exactly what to do.
You also have to realize that strict conventions matter immensely to the people grading your papers. You cannot be sloppy. We're talking proper, correct terminology, flawless formats, and clear annotation. In the control tower, we deploy the Peel formatting template to guide our communications back onto the glide slope. Point, evidence, explanation, link. While that's usually for essays, in mathematics, think of it as state the process, write the equation, execute the steps, and link it back to what the question actually asked. Make your dy by dx or f prime of x notation undeniably clear. If a multi-part question demands exact values involving natural logs or trig functions, and you spit out a rounded decimal, you just crash the plane on the runway. The examiners are heavily scrutinizing your data interpretation and presentation skills. Your clear annotations act as literal runway lights, guiding the examiner safely through your logic so they can award you every single method mark you deserve.
Section 4. Critical analysis skills. Evaluating the complex problem.
Okay, it's time for an interactive runaway workshop for all you viewers. I'm initiating live audience tracking right now. We are going to run Assessment 1. Imagine a complex data map on your radar. A massive differentiation word problem combining exponential decay with a trigonometric oscillation. I am putting a 60-second visual timer on the clock in your mind right now. Your job? To isolate the primary trend variable. This is what separates passing candidates from the top 1%. The top operators use a deconstruct, solve, and evaluate method. First, you identify the given information, strip away the noise. Second, break it into logical, bite-sized steps. Third, solve it systematically without rushing like Router Sam. Fourth, check for reasonableness. If your rate of change for a cooling object is a massive positive number, your radar should be flashing red, right? And fifth, if the question requires it, make mathematically justified recommendations. The ability to break down the complex data map into these 5 distinct steps under extreme pressure is your ultimate superpower in this exam.
Moving to Assessment 2 in our runway workshop. We call this Debris on the Runway. Your objective is to spot the exact line in a candidate's answer that violates safety regulations and drops massive points. Look at the contrast between these two approaches. Lower-tier candidates always provide generic answers. They spot a sine function, they differentiate it to cosine x, and they completely power down their brains. That's debris on the runway. It causes a blockage. Top-scoring candidates, however, utilize context-specific evaluative thinking. They question the constraints. They consider the domain limits, like if x is only valid between 0 and pi. They relate their mathematical findings, perhaps the exact stationary point of that e to the x curve, directly back to the physical scenario the question outlined. If the question is about the velocity of a particle, your answer shouldn't just be x equals 2. It needs to be understood and communicated as a specific velocity at a specific time. If you leave generic debris on your exam paper, you will absolutely lose those final critical evaluation marks.
Section 5.
Top examiner warnings. The most critical pitfalls you must avoid.
I need everyone to slow down and listen very carefully. I am turning on the amber warning lights in the control tower right now. These points aren't just my opinion. They are pulled directly from Cambridge Principal Examiner reports. These are the exact black box recordings of where thousands of students crash and burn every single year. Warning number 1, forgetting proper mathematical format and bleeding out easy basic marks. Warning number 2, forgetting to double-check that format and presentation before rushing on to the next problem. Sam does this constantly. But warning number 3 is the absolute fatal error, providing answers that are not specific to the context given. It is a massive red flag. You absolutely must tailor your final derivative, your final calculated value, to the exact constraints of the problem sitting in front of you on the desk.
To really hammer this concept home, listen to this direct, intercepted alert from the examiner's headquarters. The classic mistake is providing generic answers not specific to the question context. Always link every point to the given scenario. Let me say it again so it sinks in. Contextualization is non-negotiable. It is the mandatory final clearance for touchdown. Your procedural execution of the product rule on e to the x and natural log of x can be a work of technical perfection. But if the problem is a modeling question about population growth and you just circle a number at the bottom without linking your evaluative point back to the population scenario, the examiner physically cannot award you the final marks. You flew perfectly, but you missed the runway completely.
So we're coming in for a safe touchdown. Router Alex and Router Sam finally managed to log a successful, full-mark landing sequence by following our procedures today. But what about you? I want you to seriously evaluate your current study habits. Does your personal procedural framework guarantee context-specific answers? Are you using the fuel-to-mark budget formula efficiently? If you aren't absolutely sure, then before you tackle your next past paper, you need to recalibrate. Focus heavily on securing your method marks, perfecting your presentation, and always checking your context. All right, Tower Director, signing off. Here is your final operational command. I need you to subscribe to Ace the Exams at the handle @AceTheExams. Enable that notification bell so your radar is always active, and drop down into the comment section right now and tell me which specific exam paper gives you the absolute most anxiety. Share your coordinates in the comments, and we'll tackle it together in the next simulation. Stay sharp out there.